As I mentioned at the beginning of lecture 29A, here in lecture 29B as well, we are going to be starting to transition at the very end to the home stretch of our course, hopefully finishing by lecture 36. In 29B, we do something we looked at in lecture 28B, matrices that have complex eigenvalues, and we're not going to diagonalize them over the complex numbers like I did talk about in lecture 28B, but we're converting them to what's called real canonical form or real normal form in the case where they have complex eigenvalues. In this lecture, I'm going to focus on the geometry of what's going on with these particular linear transformations. Then I'm going to transition into orthogonality and its applications. That's what we're headed toward more long-term here to the end of the course, including coming back eventually to talking about symmetric matrices and orthogonal diagonalization, and hopefully, if we have time, also talking about partial differential equations and how that's actually related to dot products in its more general form called inner products. That's what is to come. All right, I'm going to make a real big point to try to get to a little bit of partial differential equations here in the lecture B's, not the lecture A's. So let's look at the example from last time. More on change of coordinates and similarity. Not diagonalization in this case, but converting to a similar matrix that is nicer. Recall the example from 28b, this matrix right here. Actually, it was one of two matrices we used in lecture 28b. This matrix has complex eigenvalues. What are they? They are -1 plus or minus 2i. I didn't put the plus or minus there on purpose. It's not a typo. I could deal with -1 plus 2i, but it turns out to be just work out a little nicer, geometrically speaking at least, if you use -1 minus 2i. Though there is still going to be also something confusing about this here in a little bit. The corresponding eigenvector, as a complex eigenvector, is this one. And we separate it, as usual, into its real and imaginary parts. The real part plus I times the imaginary part, both the real and imaginary parts themselves are real vectors. What do we do with this? In 28b, we put these two column vectors, two real column vectors, in a 2x2 matrix, called it P, and that was our change of coordinates matrix. By the way, change of coordinate matrices here are related to change of basis back 10 lectures ago or so. The change of coordinates matrix formed by the real and imaginary parts is this. P is this. Notice this is the first column, matches this vector, 5, 3, and the second column, 0, 1, matches this vector, 0, 1. That's our change of coordinates matrix. Its inverse is this. A similarity transformation to real canonical form, also known as real normal form, is this. P inverse AP does not end up being diagonal. This matrix A is not diagonalizable over the real numbers. It is over the complex numbers. Again, that was a subject in 28b. But over the real numbers, you can't diagonalize it. However, you can get it to a kind of nice form, this form right here. Calling this matrix C, just because I need another letter, and C does stand for complex, and that reminds me this has complex eigenvalues, but don't worry about the name. The general canonical form is this. There's some symmetry to it. The numbers on the main diagonal are the same number, and the numbers on the off diagonal are opposite numbers. In fact, you could, if you wanted to, I'll just mention this here, split this into the sum of two very special matrices, like this, where this matrix is a multiple of the identity matrix, and also diagonal, and this matrix is what's called skew symmetric, not symmetric itself, but skew symmetric, these two things having opposite signs there. Putting the negative sign in the upper right corner is arbitrary. I could have put it in the lower left corner, but it's going to be a little bit more convenient to have it in the upper right corner. For our example, then we can write the following. This is a non-obvious calculation I'm showing you here. I want to relate this to complex numbers. We're going to see some similarities to what we've done with differential equations here. Not exactly the same with forced harmonic oscillators, but some similarities. C, if you want to, certainly can be written in this way. write 1 as square root of 5 divided by square root of 5. Write 2 as 2 divided by square root of 5 times 2 times square root of 5 over square root of 5. Factor out a square root of 5 is what I'm doing. What a weird thing to do. Why am I doing that? If I do factor out that square root of 5, I do notice a pattern, a connection. Square root of 5 is the same thing as the distance in the complex plane between this point and the origin. I talked about that in 29a. The absolute value of the complex number is its distance to the origin. Another name for this is called the modulus of the complex number. That's one connection here to the complex numbers in lecture 29a. We've got our complex plane with a real axis and imaginary axis. Thinking in terms of rectangular coordinates, this eigenvalue, -1 minus 2i, you plot right there. The distance to the origin right there, that is square root of 5. Is theta in this equation, is it its argument? Actually, no, and that's one thing that's a little confusing here. Theta in this matrix, R is square root of 5, the modulus of the eigenvalue is square root of 5, but the theta is actually the argument of its complex conjugate. Remember I said in lecture 29a that argument represents an angle. It's like a polar coordinate, a theta. Technically the argument by standard convention in complex analysis goes from negative pi to positive pi, not 0 to 2 pi actually. This complex number, the complex conjugate of this one, the reflection across the horizontal real axis, so this point here is -1 minus 2i, and this one right here is -1 plus 2i. I hope the red is showing up okay. The theta in this equation is this angle, that positive angle right there, or any multiple of 2 pi added to it or subtracted from it. If you want to use the inverse tangent function to find that angle, because it's in the second quadrant, when you take the inverse tangent or arctangent of the imaginary part divided by the real part of this complex number, you would have to add pi to it. Because that complex number up here in the second quadrant has an angle bigger than pi over 2 and less than pi. The inverse tangent function doesn't give you outputs in that range. It gives you outputs between negative pi over 2 and positive pi over 2. And with the negative quantity in there, it's actually going to be between 0 and negative pi over 2. So to get to the right angle, we actually have to add pi to it. And if you do, you can check in your calculator. It's about 2.203 radians, which is about 116.6 degrees. It would be good to write that down, because I'm going to show you a graph and ultimately an animation that illustrates what's going to go on here geometrically. I'm doing all this to try to understand the geometry of the matrix C as a linear transformation. That's the purpose. I should have said that earlier. We want to understand the geometry of C as it defines a linear transformation. Before we can get there, let's recall a few things. I did mention the general rotation matrix by angle theta is this matrix, which was on the previous slide. Theta is arbitrary here, though, not the particular theta from over there. If theta is positive, you think of it as a counterclockwise rotation around the origin. If theta is negative, you think of it as a clockwise rotation around the origin. Multiplying this by the scalar r, which for our example is square root of 5, has the same effect as multiplying it by the matrix Ri, R times the identity matrix, which as a linear transformation is a dilation by a factor of r. Little r times capital R sub theta is the same as little r times the identity matrix, 2 by 2, times r sub theta. That is this, r times the identity matrix, and r sub theta is the same thing as before. And you can multiply these out, and you get the same thing if you just multiplied every entry in capital R by little r. But I want to think of it as a matrix multiplication because that's going to emphasize the geometry. C can be thought of as this product, where R is square root of 5 and where theta was inverse tangent of negative 2 plus pi, about 116 something degrees. In other words, as a mapping, as a corresponding linear transformation, T of x equals C times x, it represents a counterclockwise rotation by the angle theta, which is 116.6 degrees approximately. That is the matrix on the right, followed by a dilation by a factor of r, which is square root of 5, which is about 2.24. Okay, so again, write these numbers down. Write down theta and r at least. What are the implications for dynamical systems? When I say dynamical systems, I mean continuous differential equations and discrete difference equations. The geometry of C, the linear transformation defined by C, does have implications for understanding the vector field for this system of differential equations. And I'm using U because it's like the new coordinates. It does have implications for that. However, the implications are not very easy to understand. I think I will try to talk about them some, maybe in lecture 30B. However, the geometric connections are more clear for understanding the solution of the system of difference equations defined by C times un equals C times un minus 1. That's more clear because when you iterate this function, the geometry is evident. You keep applying, multiplying by C. So whatever geometry C has, which we already know, it's a rotation by about 116.6 degrees and then a dilation, expansion by a factor of square root of 5, which is about 2.24, that's going to happen. This can be visualized in Mathematica. Here's a static picture of an animation I made. Try to show you the animation itself as well. N here just represents the number of iterations that I've done. It's 4 here, so I started with an initial point, x0, which is this one right there. In fact, it's 1, 0 is what that is. x0, oops, equals 1, 0. Went from black to green, or green to black. This point right here is x1. C times x0, C times the vector 1, 0, which if you think about it, is the first column of C. Negative 1, 2. Or if you wanted to think of this as the complex plane, which you could if you wanted to, negative 1 plus 2i. That other eigenvalue. Yeah, it's a rotation by the argument of the eigenvalue, about 116.6 degrees. And an expansion, a dilation, further away from the origin by a factor of square root of 5. It's more than 2 times further away from the origin than this vector is. Then I apply it again. I get that point. That's x2. x2 would be C times x1. C times negative 1, 2. You can figure out what it is. Looks like it's approximately negative 3, negative 4 maybe? Somewhere close to that. It's another 116.6 degree rotation and another expansion by a factor of square root of 5. This is more than twice as far away from the origin as that is. The next one gives you another 116.6 degree rotation, another expansion by square root of 5. This is x3. Another rotation by about 116.6 degrees and another expansion by about 2.24 gives you, to this point, that would be x4. I'll show you the Mathematica for this. This is just confirming the similarity transform to normal form. Not diagonal form, it's not a diagonalization, but it is a similarity transform. to a matrix that is similar to the original. This just defines my linear transformation by multiplication by c. I had to use a lowercase c in Mathematica, by the way, because Mathematica reserves uppercase c for something special. This line is just using nest list to generate the points for an arbitrary initial condition and an arbitrary number of iterations. So I actually haven't used this yet. I just defined it. I could use it like this. I could go c data 1, 0, 4 iterations, x0, x1, x2 is what I guessed. -3, -4 if you write it as a column vector. x3 is 11, -2, 11 to the right, 2 down. Write that as a column vector if you want. And then the last one, x4, -7, 24. This code visualizes it, makes the animation. So I started with an initial condition at 1, 0. I can step forward and see the point keep getting rotated. If I go to n equals 5, it's too far to see, but I can make my r bigger. My r represents the distance between the origin and the extremes along the axes. It's 46.4 at the moment. Now we can see them all. Then I also put a locator in here. The syntax right here. It allows me to move my initial condition wherever I want. And the transformation is still the same, no matter what the initial condition is. To get to the next point, you rotate by about 116.6 degrees, and you multiply the distance by square root of 5, which is about 2.24. Okay? So the behavior here is a rotation with a dilation, a rotation and expansion. Is it the same behavior as you would get with the matrix A? The matrix A, right here. No, it's not. But they'd be somewhat similar. There'd be a rotational and dilation effect somewhat, but not as pristine, not as exacting as it is for the matrix C. All right, for the rest of the lecture, we're going to focus on definitions and theorems related to dot products and orthogonality. Some of this stuff I've shown you already a while ago. We are going to be thinking in the general case here of n-dimensional space. We are thinking about Rn here. In Rn, if you got two vectors, x and y, that have n components, think of them as column vectors. Their dot product, recall, x dotted with y, is a number, a scalar. Could be positive, could be negative, that is found by adding up the products of the corresponding components. x1 times y1 plus x2 times y2 plus x3 times y3, etc. Just going to write it with summation notation. Summation I goes from 1 to n of xi times yi, where xi is the ith component of the vector x, and yi is the ith component of the vector y. I could be 1 or 2 or 3, etc. up through n. N being an arbitrary positive integer. So we already know about that. We know other things about it as well, algebraic properties I'm not going to mention. We defined orthogonality way back, starting in lecture 4b, I actually went and looked. We're going to start to go deeper into the subject. It's got a ton of applications. Dot products, and a more generalized version of dot products called inner products, which behave in similar ways to dot products, but can be defined, for example, on function spaces. And you can even define them using, instead of summations, you can even use integrals to define them, and that's a good thing. It's going to lead us to Fourier series and trying to understand partial differential equations, hopefully along about lecture 34b or maybe 35b. Recall, I did mention this, that the dot product can be used to define the norm or magnitude of a vector. its length, its distance to the origin. There's the formula as kind of an extended version of the Pythagorean theorem. But hey, that quantity under the square root is the same as x dotted with itself. And, I think I mentioned this before, the dot product of a vector with itself, when you're thinking of the vectors as column vectors, can also be found by taking the product of these two matrices, x transpose and x itself, where x transpose is a row vector and x itself is a column vector. A 1 by n vector, a matrix times an n by 1 matrix can be done, and it gives you a 1 by 1 matrix, in other words, a number that we don't put parentheses around typically. We just think of it as a number. The square root of that is the norm. So this does represent the distance between the point x and the origin. If you're thinking of x as a point, I'll draw a two-dimensional picture, but this is supposed to be Rn. If x is a point, this distance is the magnitude of x, the norm of x. If x is a vector, an arrow, then it's the length of the vector. The norm, in turn, can be used to define the distance between two vectors, called a metric. D of xy represents the distance between x and y, just shorthand. Distance between x and y. It's easier to think about that distance if you imagine x and y as points. If y is over here as a point, this d of xy, which is defined to be the norm of x minus y, like you can see on the screen, is the length of that line segment. If you think of the vectors as arrows and put their tails at the origin, the distance between them is the distance between their tips, their heads. Same as the length of that line segment. D does not mean derivative here. Does not means distance. Call them metric. It's worth introducing some new terminology here. It's standard terminology. This D function is called a metric. It's the norm of x minus y, but since norms can be written in terms of dot products, I could write it this way. And since dot products can be written in terms of matrix multiplications, I can write it this way. T again is the transpose. The triangle inequality he still holds. The first one, in terms of norms, I wrote way back in lecture 4b or 5b or something. The length of x plus y is less than or equal to the length of x plus the length of y. Why is this called the triangle inequality? Thinking in terms of arrows, if this is x and this is y, and I think about the parallelogram law for vector addition, this is going to be x as well, and this is going to be y as well, and this vector is going to be x plus y. And if you just focus on one of these triangles in this parallelogram, say this one, by saying the length of x plus y is less than or equal to the length of x plus the length of y, you're saying the length of any side of a triangle is less than or equal to the sum of the lengths of the other sides, which is also equivalent to saying the shortest distance between 2 points is along the straight line between them. Proving this needs to be done symbolically, though, and it's not as easy as you might hope, but it's definitely possible. So you can write the triangle inequality in terms of norms. You can also write it in terms of metrics. Though you have to add an extra vector in there, z I called it, where z is arbitrary. The distance between x and y, think of them as points. These 2 points here and here. That distance there. When z is any other point in the entire space, doesn't matter where you pick it, that's z. That distance is less than or equal to the distance between y and z, between their heads, plus the distance between x and z, the distance between their heads. And now it's completely obvious in this picture that this is true. It would be maybe less obvious if z was closer in, maybe between x and y in that parallelogram. There's a Pythagorean theorem. Two vectors are orthogonal, perpendicular, assuming they're non-zero, if and only if the magnitude of x plus y squared equals the magnitude of x squared plus the magnitude of y squared. And certainly if you've got these vectors being perpendicular, and if you draw them like this and this, that's x and this is y. This is a right angle, then you've got a right triangle. This would be x plus y. And the Pythagorean theorem says that the length of this side squared plus the length of that side squared equals the length of the hypotenuse squared, which is exactly what that equation is saying in the symbols. Not proving these things, but they should make sense when you think about drawings or think about examples. More definitions and theorems. Let W be a subspace of Rn. Again, we're headed toward applications of orthogonality, especially with symmetric matrices and topics related to that. The orthogonal complement of W, written like this, a W with a perpendicular symbol as its superscript, not a number, just a symbol. You verbalize this symbol by saying W perp for short. This set is the set of all vectors in Rn that are orthogonal to all the vectors in W. It's called the orthogonal complement. In set builder notation, you can write it this way. W perp, the orthogonal complement of W, is the set of vectors in Rn such that, with the property that x dot W is the number 0, the scalar 0, for all vectors W in the subspace capital W. If we're in a situation where where we can draw something, let me pretend to draw a three-dimensional space here. If W happens to be a plane through the origin, that maybe looks about like this. Pretend that goes to the origin. That's W. W perp, the orthogonal complement of W, is going to be a line through the origin perpendicular to that plane. On the other hand, so this is W perp. On the other hand, if W is the line through the origin, then W perp is going to be the plane. The orthogonal complement of the orthogonal complement of W is W itself. Theorem: a vector x in Rn is in W perp if and only if x is orthogonal to every vector in a set that spans W. For example, a basis for W. So that's nice because it means you only have to take the dot product of x with basis vectors. If those dot products are all 0, then you know x is in the orthogonal complement of W. Another theorem: if W is a subspace of Rn, which I'm really assuming at the very beginning, then W perp is also a subspace of Rn, as I suggested with the picture over there. Another theorem, what I just mentioned a minute ago, W perp is W. The orthogonal complement of the orthogonal complement of W is W itself. These are all fairly obvious geometrically, you might say. I mean, you have to use the subspace test with this one. And to use it, you have to use the defining property of this thing. Another theorem is that if you add the dimension of W to the dimension of W perp, you get n, when these are subspaces of Rn. That should make sense too. 2 plus 1 is 3 in the picture. Another theorem: let A be an n by n matrix, then the orthogonal complement of the row space of A is the null space of A, and the orthogonal complement of the column space of A is the null space of A transpose. And these were the 4 fundamental subspaces that we talked about, maybe 5 lectures ago or something. I don't remember exactly. Thinking about a matrix A, That is m by n. Let's pretend m is bigger than n. So we got a sort of tall and skinny matrix like this. This is A. Y is the orthogonal complement of the row space equal to the null space. The orthogonal complement of the row space is all the vectors that are perpendicular orthogonal to the vectors of the row space. Those will be exactly the n by 1 vectors whose dot products with the rows of A are 0. And the row space of A is the subspace spanned by the rows of A. A basis can be found from the rows of A. With this one, you think about the transpose. The transpose of A, if m is bigger than n, is going to be longer and skinnier here. What's its null space? Well, it's going to be vectors in the column space of A because the columns of A become the rows of A transpose. And so when you take their dot product with elements of the null space of A transpose, you got to get 0 by definition of the null space. I think this might be our last slide. Yes, it is. More definitions and theorems. We need to build up the theory here toward our applications again here. Let S be a set of vectors that are non-zero, P vectors, and mutually orthogonal vectors in Rn. The dot product of any two of them, distinct ones, is 0. When that happens, we define S to be an orthogonal set. That's essentially a definition within the theorem. When that happens, we say S is an orthogonal set. The conclusion of the theorem is that S is a linearly independent set and is therefore a basis for the subspace spanned by S, the span of S. If P happened to be n, then the span of S would be all of Rn. But if P is less than n, then it won't be. The main conclusion is it's a linearly independent set, and therefore by the basis theorem, really. Well, actually by definition of basis. It's a linearly independent set that spans this subspace, call this W if you like. Therefore, it must also be a basis of that subspace. Another definition, let W be a subspace of Rn. An orthogonal basis for W is a basis of W that is also an orthogonal set. So it is a basis and it's an orthogonal set. Distinct vectors in it are orthogonal. Their dot products are 0. In terms of change of coordinates, this basis of orthogonal vectors would represent axes that are all perpendicular, which doesn't always happen with our change of coordinates. Here's a big theorem. This is the most important one, perhaps. Let x1 through xp be an orthogonal basis for a subspace W of Rn. Then for each y in Rn, that's a typo. Each y in W. And I think there might be a typo in the next line too. We can write y as a linear combination of those vectors in this way. Actually, no typo here. Y is this fraction whose numerator and denominator are dot products times that vector, which is a vector, plus this number times this vector, which is a vector. These are scalar multiples of the basis vectors, etc. through this one. Don't these look kind of familiar? They should, actually, if you go back to lecture 5b. These are projection vectors. Each term in this last equation is a projection vector of y along the line through the corresponding vector xj. This is the projection vector of y along the line through x1. This is the projection vector of y along the line through x2. What were projection vectors? In a picture, say, two-dimensional picture. And we are in the case where we're assuming these vectors are orthogonal to each other and non-zero. So maybe x1 looks like this, and x2 is some other vector perpendicular to that one. Right angle there. If this is y right here, what is the projection of y along x1? Drop a perpendicular line from the tip of y down to the line through x. And the projection vector is this vector right there. That darker vector is y dot x1 over x1 dot x1, which is a scalar, times the vector x1 itself. And I can do it, a projection along the line through x2. That's a right angle as well. And then this vector is the projection of y along x2. It's y dot x2 over x2 dot itself. That's scalar times the vector x2. And I could try to draw a three-dimensional picture as well, where x1, x2, and x3 would all be mutually orthogonal. And so it would kind of be analogous to x, y, and z axes, which are mutually orthogonal, but it might be rotated in some way. New coordinate system, maybe. We can think about it that way. What's the point here? The point is these coefficients the multipliers, the scalar multipliers of the vectors are easy to find. You don't have to bother solving systems of equations to find them. That's the answer. Might have time for a proof of that in the next lecture, but I'm not sure. That is the last slide. I don't think there was anything else on Mathematica that I wanted to show you. So that is the end of lecture 29B. Have a good day.